Okay, I think it looks like we are full. So
Yep.
it's a great pleasure to have today Nicolas Tapia, who is going to present his work on branched Itô formula and natural Itô-Stratonovich isomorphism. Please.
Okay, thank you, Koresh, for the introduction. Yeah, so this is joint work with Carlo Bellingeri and Emilio Ferrucci, and it's about some interesting facts we managed to prove about branch of paths in general that were somehow, interesting for a number of reasons, which I'm gonna try to convey to you during the talk. So first, let me start by just setting up some notation. Before I fully begin, I want to say that this talk is very heavily based on the concept of branch of paths, and then if you're not comfortable with it, I apologize, but I don't really have the time to introduce everything, so I'm gonna give a very quick introduction, like 1 or 2 minutes. But that's all I can do given the amount of time I have and the sheer amount of things I have to present. But anyway, if you feel like you don't understand something, just feel free to let me know either in the chat or by just unmuting yourself.
Maybe your slides seem to be a little bit cut off. Maybe now it's better. Yes, thanks.
Okay, sorry. Yeah, it's one of the downsides of having 2 screens. Okay, so right. So that being said, just setting up some notation, I'm gonna work with the Connes-Kreimer Hopf algebra of decorated rooted trees. So decorations are first, as usual, just some elements from a finite set, and then later in the talk they will become actual vector spaces or elements in a vector space, more precisely. Its dual I will denote by HGL. So this is the Grossman-Larson Hopf algebra, where this product here is dual to the Connes-Kreimer coproduct, defined in terms of cuts. And GL is the dual to this forest product. So it's just a free co-commutative product on the trees. Right. So I'm gonna consider also shuffle algebras in the second half of the talk, like towards the end. And so I will denote, given a vector space, so this would be the letters or the primitive elements. I will consider this shuffle V, which as a vector space is just the tensor algebra over V, so the direct sum of all tensor powers of V. The product is the shuffle product, and the coproduct is the deconcatenation coproduct with respect to the tensor here. And I'm gonna be using throughout sumless Sweedle notation. So whenever you see sub indices means coproduct, and with upper indices means a reduced coproduct. Okay. So what are branch of paths now that we set up all this notation? So they are basically a map into the Grossman-Larson Hopf algebra, such that they are group-like for every S and T. So this is a family, 2-parameter family of group-like elements, meaning, and I'm going to introduce the notation now, meaning that whenever I take X on a product of a forest F and a forest G, evaluating some ST, this is just like this. Sorry, G. Yeah, so this is one thing. They should satisfy this relation that is known as chance relation. Given a relation between the value of X in some S and U and UT, and you take the Grossman-Larson coproduct and you get the thing over the whole interval, so to speak. So this is supposed to be mimicking some properties of integrals. And there is some analytic condition that I'm not gonna go into because this would not be the interesting part of the talk. So the main reason why I would want to introduce this kind of object is to look at differential equations that are driven by paths that are non-smooth or don't satisfy any nice properties, right? So for example, if X was just a smooth function, this would be an ODE, and then I could use, for example, P series to get a somehow local expansion of Y. If X was a Brownian motion, I can still somehow use Itô calculus and also get a notion of solution or some way of knowing the local behavior of Y in terms of X. But if I don't have any of those tools, these three conditions here are supposed to replace exactly what is needed to still make sense of this equation, at least as a local expansion in terms of x for t close to s. So this twiddle is going to appear in a few of the slides, and it just means this is not an exact inequality, but it's true up to some small remainder that vanishes when t gets close to s. So this is the analytic part that I'm just skipping through the talk, but it's always gonna be used, right? So this, so if, for example, x of st was just t minus s somehow, so this dx was just dt, so we had an ODE. For a forest, this would be like t minus s to the number of nodes in the forest divided by some combinatorial factor, which I might not get totally right, but this is somehow in this sense a generalization of B series. So if I put this here, I would have actually a B series. And there's probably a symmetry factor here also. But otherwise, somehow this map X is abstracting the properties of the iterated integrals such that this still works in a nice way. And there is also another analytic tool that I'm not gonna mention, but just so you know that it's there. It's called the Sowing lemma, and it allows me to interpret this local expansion really as some form of abstract integral. So I can also rephrase this equation here as some form of integral equation, as you could also do with an ODE. So we can say that y solves this equation either if it has this form or if it solves this integral equation. And here you can see that I somehow switched from standard y to bold y. And this is because I don't only need to include somehow the actual y that was here, but I need to include derivatives of y with respect to x that are encoded in these elementary differentials. Okay, so more or less in a nutshell, this is what rough are supposed to be doing. And we are interested in two things. So one is an Itô formula, and the other thing is going from Itô to Stratonovich integration. So as I mentioned, these are, for example, x could be a Brownian motion. Then I have a solution to this ODE, and I can apply a smooth function to y, and I know that this transforms in a certain way. And I know that if I have phi of y, I can write this as a sum of integrals, again, with some differential operators acting on phi, and some integral with respect to Brownian motion, its quadratic variation. And I would like to know if such formula is possible here when I don't have Itô calculus available from the start. Yeah. And so this is a problem that's been looked at before by some people. And the basic idea is the following. So again, let's suppose that I have an RDE like this, as defined in the previous slide, and I take an observable, and I try to see what the value of phi in y looks for t close to s. Now again, I have the twiddle here, and this means that I can apply a Taylor expansion. So this first follows by Taylor. So I can just Taylor expand phi in terms of y. And so here I get phi prime, and I get the increment of yt minus ys. And if I go to the previous slide, like this is one of the first terms you will see here, and also the one you would expect in the B series expansion, right? So yt minus ys up to first order is just the vector field frozen in the left point of the interval times t minus s. So this is like another one Taylor expansion of y now, not of phi, but of y. And I can continue with this since I have a full B series. So the next term would be this, right? So here you again recognize maybe the elementary differential associated to these three, but I still get second derivatives coming from Taylor's formula, and now I start to get forest here. Right. And so this is just Taylor's expansion up to some more terms that I'm hiding here. And now I would like to say that this is a sum of integrals, like you would have in for Brownian motion, for example. And this is where sewing enters. And sewing requires you to have a very precise description of the thing you want to put inside the integral, at least for t close to s, in order to be able to actually build this integral here that was the one appearing also at the bottom of the previous slide. So, so the fundamental thing to notice here is that while I would like to say that this integral here is the limit of this part that I got here, which is somehow the only part depending on phi prime, right? Here, this is depending on phi second already. I cannot say this immediately because the sewing lemma, as I said, requires a very specific form of this. And what's needed is actually that the term in front of the next term needs to be the actual derivative of this guy. And if you look closely, this term here is almost the derivative of phi prime f, except that I'm missing one derivative of phi here. Right, and but I can just insert it, right? So I can just say I have the correct term, and then I get some reminder that gets pushed into the next correction, right? So all I did here was just write this, and then this -2 comes from this 1/2 here, right? So I did nothing. I really added a 0, basically. And now I can apply sewing to this thing, and I get an integral. And if I was able to also make sense of this integral, or say this is an integral, then we would be done, because now I can say this is one integral plus another integral plus etc., etc. And this starts to resemble an Itô formula. So David Kelly observed that actually this thing here, this polynomial in X that I got now, is actually a path. So it's not a proper two variable thing, but it's actually an increment of a path. So in the sense that x is t dot dot -2 this can be written as some path evaluated at t minus some path evaluated at s. So this is the fundamental observation, that for some linear combinations of forests, I actually recover paths. And so if I have a path, I can start thinking about integration. And this is basically what he called the bracket extension, which is just a set of assumptions that allows me to interpret now this as a proper integral. And if I can do that, then I can write this formula now. So phi of yt minus phi of ys really looks like the integral of some differential operator, namely f applied to phi, plus some second order differential operator applied to phi, plus times integral of a different path, which for Brown motion, this would be just dt. Right? So at least making doing this trick allows me to write the value of phi in y as a sum of integrals. Okay, and he called this the bracket polynomial. So now the question is, how do we find these polynomials? How do we characterize them? Right? Because this was more or less a simple computation, but if you have bigger forests and you want a systematic way to characterize these elements. And it turns out that at face value, the answer is quite simple. So it's by observing that chance identity that I showed you before that is satisfied by the rough path, when you evaluate it in a forest, it actually means this. So you see, if you take these two guys here to the right, this would be just the coproduct of applied to f, then evaluated in XSU tensor XUT, right? So this is exactly what this convolution product means. And then I can take the primitive part to the left, and I get now this condition. XST f minus XSU f minus XUT f. So this looks like some delta operator, if you know what I'm talking about, that appears quite frequently in rough path theory. Is equal to the reduced coproduct of f. So for example, if f is a primitive element, meaning that the right-hand side is 0, this means that this is 0. So if we are primitive, and this means that xf of st is again x some path. So f of s. So essentially, what I can do to find increments of paths inside my row of path is look at primitive elements. This will give me always an increment by this chance identity. So as we saw before, we can try to find by hand these primitive elements. So this is 1 now in the decorated case. So the 2 here got replaced by a symmetrization. Here 1 in the labels, 1, 2, minus 2, 1. Then if you look at order 3, you can still do this by hand, and you get this. But then the question is how to continue. How do I find these primitive elements? And this answer was given by independently by Broadhurst and Kreimer in 2000 and Loic Foissy in 2002 by introducing what's called the natural growth operator. Which is defined as grafting the forest F onto every node of G simultaneously. So this is not the Prilly grading, the Prilly grafting that you might have seen before, but it really grafts everything onto a single node. It doesn't graft different connected components of your forest into different nodes. Right, so for example, just to see the difference here, I have this forest grafted onto this stick, and I graft either onto 4 or onto 3, but I don't do this. I don't do this, right? So for example, I could graft 2 here. This is 3, 4, 1. This term doesn't show up. So in this sense, it's not the Prilly grafting, and actually it doesn't satisfy any nice relation as far as I know. It's not associative. It's not defining some kind of nice product, but still useful for what we want to do. And so the first observation is that if you pick a primitive element and you define this operator IP on a forest by just natural growth of F into the primitive, then you get a 1 cocycle. And as you may know, 1 cocycles are tightly tied to integration. Yeah, I'm going to explain this in a few slides, but they are somehow maps that are abstractly representing integrals in some sense. And this generalizes actually the B plus operation that's present in the Connes-Kreimer Hopf algebra to any primitive. So I can really graft onto not just single nodes, but full primitive elements and get a similar behavior, at least algebraically. Okay, so what can I do with this? For example, the first theorem is give me some structure theorem for the Connes-Kreimer Hopf algebra, which is the following. So I can take now the tensor algebra over the primitive space, and I can map a tensor product of primitives onto this left bracketed T operations. So this is just Pn T Pn minus 1 T Pn minus 2, like this. And this gives me an isomorphism of coalgebras, which is nice. So I can really think of the Connes-Kreimer coproduct acting on forests that are written like this as just being a type of deconcatenation coproduct. So this gives me an easier way of computation, modulo that I can find a nice way of writing my forest as T of primitive, which is not completely obvious. But still, this is some kind of structure theorem for this Hopf algebra, which is somehow explaining how to decompose forests in terms of iterated integrals in some sense. Okay, so observe that, as I said before, if I take I with a single dot, which is a primitive element, then I recover the B plus operation, but I need more than this to get the covariance. So I actually need the IP for every primitive, as Loic showed in 2000s. So every time you have a coalgebra that has a family of operators indexed by any primitive, like this, and satisfying the 1 cocycle relation, then you can show that C is actually co-free over its primitive elements. Yeah, so actually this result just follows from this. So, and in this particular case of the Connes-Kreimer Hopf algebra, the IP operations are constructed with respect to the natural growth. But in general, if you can find these elements, you have a similar result. Okay, so now the question is, I have a nice way of decomposing at least partially the Connes-Kreimer Hopf algebra in terms of primitive elements. So again, how do I find these primitive elements? And the answer is, I have a projection from forests, so any element in the Connes-Kreimer Hopf algebra, onto the primitives, recursively defined like this. So this uses the reduced coproduct, as you can see here, applies pi1 recursively to the right factor, and then applies the natural growth operation in the middle. So now we go back to the examples we found by hand, and you can check that, for example, pi1 of this forest 1, 2 is the one we found before that Kelly found somehow when trying to do this Itô formula. And you can see somehow the symmetry of this forest now is reflected on the form of the primitive element. So this is symmetric in 1, 2. And so therefore, this guy is also symmetric in 1, 2. This guy applied to the 3 dots now is the symmetric one that I showed here, right? It's also fully symmetric in the labels, and this is now explained by the fact that it comes from the projection of a symmetric forest. But I can get some more relations. So for example, I can get pi1 of a forest like this, and I apply recursively my formula, knowing that I know these guys, and I get this expression. And if you look closely, then this is antisymmetric in the labels 1 and 2. So for example, here and here you can see the antisymmetrization. Here and here you can see the antisymmetrization, and also here. And this is not immediately evident from the form of the forest. So here it was more or less expected that this would have to be symmetric because the forest on the left is symmetric, but here, yeah, I don't know. So I don't know if there is a way of getting a priori all the relations that you would get from pi1 of forests when you change the forest in terms of decorations or whatnot. I mean, I don't know. You know, so if you give me a forest, I cannot tell you what kind of symmetries pi of this forest would satisfy. But as you can see, you get some relations once you compute it in some examples. And there is also a non-recursive formulation of this pi1, which is just by unraveling this recursion. It can be done explicitly. Okay. Right. So why is this nice? It's because it somehow formalizes what I was saying before, that you can decompose the Connes-Kreimer Hopf algebra in terms of iterated integrals in the following way. So now you can get a series of projections by n, which are really taking the nth iterated coproduct, applying a pi1 projection on each factor, and then applying t in the middle, replacing tensors with the t of the natural growth operation in the correct order. So always from the left. And this satisfies a series of properties. So for example, they are in some sense orthogonal to each other. So if you project with m, then you get something that's completely independent from the nth level, and if you take n equal to m, this is just a projection onto some space, and otherwise they are unrelated. They actually decompose the identity map. So if you sum all of them, you get back your original forest, and they actually behave like a deconcatenation in the sense I was saying before. This is just coming from the isomorphism as coalgebras property that I mentioned before. So basically, this is telling you that, in a sense, pi n is the projection onto the nth tensor level in terms of primitives. But this is now internal to Connes-Kreimer, right? So you take a forest, which might be complicated, and it decomposes it into its grafting of primitives, which is what I showed you. I told you before we had to do, right? So if we had a nice way of decomposing any forest as iterated natural growth operations of primitive elements, then we are in a good shape, because we are somehow we have an easier way of computing with things like the Connes-Kreimer coproduct simplifies to a deconcatenation, and so on and so forth. And so this is the way to achieve this at these higher projections. And in particular, we actually get a full decomposition of the Connes-Kreimer Hopf algebra into subspaces that are somehow can be thought of as n tensors. So actually, you should think of this space here as P tensor n. So this is really decomposing the Connes-Kreimer Hopf algebra as words of primitive elements. Yeah, modulo this natural growth operation. Okay, and this is going to be important actually for the Itô-Stratonovich conversion. Okay, so some interesting facts. And how is this related to integration? So for example, if you take two primitive elements and apply the projection to them, so the product of two primitives is in general not primitive, and you can look at the primitive part, then all you get from the recursion is three terms. You get the product. This is always present, right? So the recursion starts with f itself, so this is fine. And then by primitivity, you can see that it stops after the first iteration, and you get actually this formula, which you can then turn around and say, okay, the forest product between P and Q can actually be written as some shuffle product, some shuffle-looking product, right? So this is P shuffle Q in some sense, if we're thinking of T as being words, as I mentioned before, right? So this gamma isomorphism tells me that whenever I see T, I can just think that it's a tensor. So this plus some contraction term. So this is now a primitive. So I'm multiplying two primitives. I get a worth of length 2 and a worth of length 1. Right. So and this looks suspiciously close to a quasi shuffle product, where somehow this is the contraction part. And this is the reason why we are able to show the Itô-Stratonovich isomorphism. Yeah, I'm going to explain this later, but somehow this is what's underlying all this. And now if we go back and think of these guys indexing some iterated integrals of my x, then this is telling me that modulo this correction, x satisfies integration by parts up to some increment, which is somehow, again, a type of Itô rule, right? So the Itô rule is saying if you multiply two semimartingales, then you can write the cross integrals plus some correction, which is the quadratic variation. So in that sense, this is also somehow an algebraic form of the Itô formula. Yeah. So somehow already we have all the ingredients we need to prove these two results. And in general, if I multiply bigger forests here or more complicated forests, which is not just product of two primitives, but some arbitrary forests, then I can still get a complicated expression in terms of only T and pi 1. So this is telling me how to write, in this interpretation, this is telling me how to write the forest product, the product of two integrals as a series of iterated integrals plus corrections. And this is what's known as a B-infinity algebra. So quasi-shuffle algebras are a particular case of a B-infinity algebras, which is why this product here looks like that. And in general, if I have more complicated products, I can still write a formula like this. And this will satisfy what's called a B-infinity relation. Okay, again, I don't have time to go into all the details, but these are explained in our preprint. So I would just refer you to that. And then, again, if you are in a semi-martingale case where we can do actual computations, like more explicitly just these algebraic formulas, then we see that, for example, this pi 1, this interpretation here was somehow correct. So if I take the pi 1 of a product of dots, then I really recover this needs to be an increment because it's a primitive element, and this is just the increment of the quadratic variation of the in the interval st from s to t, and it's 0 otherwise. So, which is more or less in line with the fact that we have a classical Itô rule. And if I have an arbitrary forest, actually what happens is that integrating this complicated object against one of these paths indexed by primitives, I get this can be written in terms of this natural growth operation. So in this sense, natural growth is representing integration. And in fact, this one cocycle property is actually tied to the fact that this is an integral. Since I can just split the interval in some midpoint u, go through the computation and see that up to a remainder, this is essentially the one cocycle property telling me that f grafted onto p, it splits the integral according to the convolution product. Yeah. So in that sense, the T operation again is somehow representing an abstract integration. And we use this idea to encode Davy expansions, so solutions to differential equations in a bit more general sense that we started before, where the driver now can not only be X itself, but it can have vector fields in the direction of the primitive elements. So again, this is somehow reverting or building, I should say, on the idea of Itô calculus. So where I could have some some sigma in front of the Brownian motion, but I could have also some mu in front of the quadratic variation. So this is a more general equation than the one I showed you in the beginning, because now we are able to handle, and we actually know that we can integrate against more things than just the base path. So that's the whole idea. And now, in this full generality, I think in the sake of, since I don't have much time, I'm just going to skip to the actual result. I can write the actual Itô formula. So I take a solution to an RDE, again, in the sense of having a particular B-series expansion. And then for any smooth function, I can write the value of phi in y with respect to the value at 0, plus a sum of iterated integrals with some differential operators acting on phi. And actually, the differential operator is a map that takes a forest and gives you a differential operator of some order. And it's a Hopf morphism between these two Hopf algebras that is defined in this way, where actually I didn't say what F bar was, but it's I have an example in the following slide, so it will become clear then. But this is some extension that you have to do first from F to go to some intermediate vector fields and then extend to differential operators like this. And so this is somehow reminiscent of Itô formula again, because you're writing the value of an observable of your solution as a sum of integrals of your of differential operators that are given by the original vector fields. So we are not introducing any extra information. We are just working with what we started with, applied to phi, times, integrated against some path, which again, given what I said previously, these are interpreted as somehow stochastic brackets of X, even though they might not exist in the actual stochastic sense. Okay, I just saw that there were some questions in the chat, but apparently they were answered by Emilio, so thanks. Yeah, and this works because the Grossman-Larson Hopf algebra is free over the image of the adjoint of the projection. So we have a free generating set as an algebra, so we can define F over this set and then extend in an appropriate way to get this. So there is a bit of work we need to do to get the actual somehow workable form of the map, but again, it can be done. So let's see with an example. Again, I tried to come up with an example that's simple enough so that I can write it in the slide. So this is an RDE where it's driven by some vector field in front of the increment. So if you want to think of an SDE, this would be sigma times dB plus mu times dt. Again, interpreting this pi as the quadratic variation, which we can do when X is a semimartingale. And what this formula we found tells us is that now first we can get an expansion of y in terms of in terms of the vector fields themselves with some corrections. So if you're familiar with elementary differentials, you will notice that this expression here is the one associated to this tree. So it's just the Briley product between these two guys. So this is F alpha acting on F beta. But I get now this correction coming from the fact that I had a drift. Yeah. And in particular, this means that this map, the map that you get here as elementary differentials from forests to these vector fields is not a polymorphism, because you can immediately check that this is not the polymorphism, since this is the Briley product of dot beta and dot alpha, and this is the Briley product of the vector fields minus something. So this is not a polymorphism. But if you restrict to the case that people have looked at before, where this is 0, then you will see that you actually recover a polymorphism. So I find this is quite interesting, because we are able to, by just using this freeness and this decomposition in terms of pi, we are able to find a homomorphism from forests to differential operators that is not induced by a polymorphism, which is the way you would usually build elementary differentials. You start with the dots, you say this maps to my actual vector fields, and then I build everything by just grafting, right? But in this case, we cannot do this because we have this extra vector field here. And yeah, by playing around with this decomposition in terms of primitives, we managed to actually get the terms anyway in terms of a morphism. And this refers to the extension F bar that I was talking about before. So I cannot just put F here, because otherwise it would basically be a polymorphism, but it's not. So you need to come up with a way of extending it first, and then you get the morphism property, but only an algebra morphism property. You don't get Briley. Okay. Right. So in the 15 minutes that I have left, I want to somehow go into the Itô-Stratonovich correction. And again, this is important because Itô calculus, while it's nice, it has some kind of complicated chain rule, which we know, and now we know that in the general case it can get quite complicated. And so we would like to work in a setting where we can just apply the rules of calculus that we know. And this is what geometric rough paths are about. And this is somehow where the shuffle algebra comes in. So again, if you want to think in terms of differential equations, this would be like solving the difference between solving again, I'm gonna be a bit redundant here, but it's the difference between solving an equation in the Itô sense or the Stratonovich sense. So we know that modulo the stochastic bracket, we can go back and forth. And there is one very precise correction that you need to do if you want to go from both worlds. And what we are aiming to do here, as I explained before, is somehow reproduce this kind of conversion in a way that doesn't really use the fact that X satisfies an Itô rule from the start. So we don't assume that X was a semi-martingale or anything, but just was lifted as a branch of path, which might be a bit of a strong assumption if you want. But then we can still go to somehow Stratonovich sense of integration and apply the usual rules of calculus. And this turns out to be an isomorphism, so which means that we don't lose any information. And there's actually, we can show that it is natural in this, and this is important for some applications, which I'm gonna mention a bit further. So as I said some slides before, we know that these two spaces now, where H of V denotes the Hopf algebra, the coalgebra of trees where each decoration is now a vector from some vector space. I mean, defined in the appropriate way. And these are as coalgebras are isomorphic. So when I put the deconcatenation product here, and I take the Connes-Kreimer coproduct, and the isomorphism is given by this primitive decomposition and the natural growth operation. So what about making them isomorphic as Hopf algebras now? Like if I want to put the shuffle product here, which, as I said before, is somehow governing the Stratonovich integration. Well, it turns out that the obvious guess does not work. So the same isomorphism cannot work. And you can come up with examples quite quickly. You don't have to look very far, and then you wonder, how can you do that? And moreover, as I said before, you would like to do it in a natural way, in a sense, in the functorial sense, where I now interpret these two guys as functors, right? So they take a vector space and give me a Hopf algebra, which in this case is constructed by decorating trees with vectors from V, and then keeping the Connes-Kreimer operations in the underlying tree or forest. And here, this is just the natural functor modulo this P, which comes from this. Okay, so more precisely, what I want to find is a natural transformation between these two functors, natural isomorphism, which means making this diagonal commute. So for every pair of vector spaces, I want to find a phi that makes this diagonal commute. Yeah. So why is it important to get a natural isomorphism and not just a isomorphism? Because the people have looked at this problem again, because this is interesting for applications, and there's actually plenty of of ways of going back and forth, shuffled and Connes-Kreimer, but they are somehow not natural, which I'm going to explain again. And why it's important that for it to be natural is because sometimes your rough path comes from has some extra properties apart from being a rough path. So, for example, if you start with some stochastic process that are just IID copies, say a standard Brownian motion, and you know that if you permute the labels in your tree, this should not change the law of the integral, right? Because they all have the same distribution, so somehow the labels should not matter. And the problem is that if your transformation is not natural, going to a Stratonovich integral might destroy this property, which is not desirable. Yeah, so you want to somehow be transformed, but in a consistent way, at least in this sense. And this is also interesting for defining rough paths on manifolds, because, again, this is exactly what you're doing. You want your definition to be independent of change of coordinates. So you want it to be covariant with respect to change of charts. And this is exactly what this naturality property is telling you. It doesn't depend on how I pick the chart, but it transforms exactly in the correct way as it should. Yeah. So this is, for example, two very immediately seen reasons why this naturality is desirable. Okay. So how do we define this map? So the strategy, as we saw overall during the talk, is to use the cofreeness property we have. So the structural theorem is quite important. And in this case, cofreeness buys us a way of defining coalgebra maps, at least between these two sets. So we know we have one coalgebra map. It's actually a coalgebra isomorphism, which is this gamma operation that is taking a tensor and inserting the natural growth in the middle. But we know it's not an algebra morphism. So what we would like to do is to look at the whole class of coalgebra maps and try to find one that it's also an algebra morphism at the same time. So somehow we need to use a bit more. Cofreeness is nice, but we also want to use the algebra part. And so it turns out that cofreeness of this space means that all coalgebra maps are completely determined by their projection onto the underlying vector space. So if I know the map, again, as freeness tells you, right, in order to know an algebra map from here to here, is you know that I only know it on generators, and then I can extend here by freeness. Like I take a psi of a product to be just the product of the psi's, and this works. Coalgebra is somehow it's dual in the sense that in order to know a map from here into here, all I need to know is its projection onto the generators. Right? It's really the dual concept. So in this sense, it depends, as freeness depends on an injection from the generators into here, cofreeness depends on a projection from here onto the generators, which is the pi one. So again, just to repeat, coalgebra maps from some coalgebra to a co-free coalgebra are determined by the projection onto the generators. And actually, this tells me that if I want to find a psi that is a morphism, it needs to satisfy this extra property. So here I can pick whatever I want. I can pick any map from forests to primitives. But if I want it to be also an algebra morphism, the projection of a forest product needs to be 0. And the reason is that shuffle only increases the primitiveness degrees. It has no contractions. So once you multiply two primitives, you get a worth of length 2. So the projection, it has no primitive part anymore. So that's the reason why we get a 0. So this is a way of characterizing bi-algebra maps, if you want, in terms of the cofreeness projection. And this only works because this guy is it's cofree. Okay, so you look for a little while, and then you realize that many of the naive choices you want to make don't work. But actually, you can somehow, we came up with this map induced by the O'Leary idempotent. The reason why we thought about this, it's because it resembles Hoffman's isomorphism, right? So we know Hoffman from quasi-shuffle to shuffle, it's some form of logarithm, and it actually has logarithmic coefficients. So it has this -1 to the n divided by n. So we thought, which maps we know are of this form? And then one of the first that came to mind was the O'Leary idempotent, which is defined like this. So this, you take the reduced coproduct of f, and then you for it multiply all the components with some logarithmic coefficient. And it would be nice if this worked. But while it satisfies this, it's not a coalgebra morphism. So I cannot just take E. I cannot just take the O'Leary idempotent to be this. But I know that as long as I have a map that satisfies this, I can generate a coalgebra morphism from it by cofreeness. Okay, so the end result is that I get an induced map such that its projection onto primitives, so its primitive part in the image of log, is given by the primitive part of the O'Leary idempotent. And then the way you induce this map is just taking iterated reduced coproducts and then applying the generating map to each of the components. This is kind of the usual way you generate a coalgebra map from a projection here. It's somehow the dual version of the lifting as products, right? So you take iterated coproducts and then so. And this gives you a map that we call log, and it's actually, you can show that it's an isomorphism between these two spaces, which is moreover natural in V. And it's invertible by some abstract nonsense. And actually the inverse is not easily computable, but it satisfies some recursion where you can at least compute some examples. And so just to show I'm not lying, I'm giving you here the exponential map, for example, for two primitives. So this is, remember, this is in the shuffle algebra. So now primitives are letters in my shuffle algebra, are in the underlying vector space. And what I get is natural growth in this order plus 1/2 a correction. And this really resembles the Hoffman's isomorphism, where if you would think of this as being a contraction in some algebra. It turns out that if I restrict to two primitives, this is actually associative. Pi1 is an associative map, meaning that pi1 of PQ, then R, then pi1 is the same as pi1 of P, pi1 of Q. And so actually this is B infinity, part of B infinity relation. So B infinity is associative in some cases, but a lot more. And for 3, this is where you start to see something different. So if you know Hoffman's isomorphism, you will immediately recognize the first line. So this is just Hoffman's. So with the sum over compositions, and you contract according to this composition and do word product here, concatenation, which in this case is replaced by natural growth. And we get an extra term. The meaning of this term is that in B infinity, I'm actually allowed to contract more than just letters. as I can in quasi-shuffle. So quasi-shuffle contraction can only contract letters from your space. But here, if you look, I'm contracting a word. So this is the word P tensor Q somehow. And this is contracted with R. And for quasi-shuffle, this is not allowed. So, or it doesn't show up, right? Because the structure you start with is an associative algebra. So it only sees elements from your algebra. It doesn't see words from your algebra. It doesn't know how to contract them. But B infinity knows, and it gives you a rule of how to do these contractions in a compatible way, such that they give you something nice somehow by algebra. And you can see here I have this double contraction, so word against letter, word against letter. And if I were to take an appropriate quotient to go back to the associative case, so I just keep this relation, I'd say all the other relations are just zero, this part would go away and I go back to Hoffman. So in that sense, our isomorphism really generalizes Hoffman to the branch of path case. And this is why we decided to call it Itô-Stratonovich correction, right? It's because it's just Hoffman is really doing the Itô-Stratonovich conversion in the semi-martingale case. And one remark that I should make is that really we never actually use that this is the pi1 coming from the natural growth operation as defined before, specifically for trees, but we only use the B infinity relation. And actually this map here works equally well when you have a commutative B infinity algebra here and not just the Connes-Kreimer Hopf algebra, where you have to replace, as I said here, you have to replace T by tensors and this pi1 by the appropriate B infinity bracket. So this is what I've written here. So essentially what we're thinking of is pi1 is really the B infinity bracket in this sense. And again, just to reiterate, quasi-shuffle algebras are an example of commutative B infinity algebras, although very simple one. And this means that our map really generalizes Hoffman's isomorphism to all B infinity algebras. Okay, and results, I think I'm gonna just briefly go over it because I'm already over time. So you can convert, as promised, between branched RDE, now with drift even, to a geometric RDE, so to a Stratonovich differential equation with some modified vector field. So this vector field that was put here got transformed by the pi1 and the Eulerian idempotent into a different set of vector fields, but now the equation is driven by a Stratonovich integral. Right, so just to quickly mention previous approaches, and since I promised that I would do this, so Hairer-Kelly in 2015 already came up with a way of going from branch to geometric, but the problem is that their map it's not an isomorphism. So you lose some information. You cannot revert back to the original equation. So you can go to the geometric side, do your computations, but there is no way to recover whatever calculations you started with. You get extra terms that are, should not be there somehow. And moreover, it relies on Lyon's Victoire extension, so in some sense, it's also non-canonical. Yeah, you can find many X bars, the geometric X bars that are representing your original branch of path. So in that sense, it's a good thing you can do it, but it's not the optimal way. And then Boedihardjo and Chevyrev in 2019 used some results on the free pre-algebra to build some isomorphism. But the problem, while they get an isomorphism which is not depending on Lyon's Victoire, the problem is that it's not natural. Because what you need to do here is choose a basis for a generating set for the free algebra, and this is not an easy way to do, an easy thing to do. And what they chose was that this basis, for example, at level 2. So if you wanted to recover the usual Itô-Stratonovich conversion, and they have to put an order here. So this is like a Lindon word. And this is not natural. So if you switch alpha and beta, this is not part of the basis anymore, and you lose the properties you want. And what we propose is that our isomorphism doesn't have this problem. So this is our contribution. We get an isomorphism that is more over natural. Okay, and just to finish, just a brief recap, and we also did some more things. We can get an algebraic characterization of whether your path was actually geometric or quasi-geometric to start with, and we can construct some examples that have non-trivial variation, like this extra variation that do not show from semi-martingale computation. So we can actually construct a branch of path that does not come from a semi-martingale path. So, yeah, but again, I don't have time to go into any of these, and we are also able to define analogs of the Kailath-Segall polynomials, which are interesting for taking stochastic exponential or doing weak products and stuff like this. We can also handle. Okay, sorry for being so over time, and thank you for your attention.
Thank you for this nice talk. Other questions?
I mean, there were already some questions in the chat.
Yes.
Yeah, maybe Darich, maybe he's not here, but
left. I think Yosha, Dr.
yes,
Yosha, you have to say something.
Yeah, if you let me just, because Darich pointed out that this looks like an really important, but it's not. It's not. It's something different. It is actually, well, you could say it's an Eulerian idempotent, but with respect to what's called an infinitesimal by algebra. So it's not really the usual Eulerian idempotent, but it's somehow modified version of it. That's why the properties look so similar, because it's an Eulerian idempotent in a different category, so to speak. Okay, yeah, sure.
Nicholas, maybe you made it clear, but yeah. So the question is, there's two parts here, right? So there's two disjoint parts. Is this correct? So the second part, you've shown that every commutative B-infinity algebra is a shuffle algebra.
Yes.
With an explicit isomorphism.
Yes.
And independently, in the first part, which is a special B-infinity with the CK or GL,
yeah,
you identify primitive elements. These are two different things, right?
Yes.
Is there any relation? So is one needed for the other, or the other way around, or no?
Well, I mean,
two papers. This is essentially what I'm asking. Yeah.
No, well, okay. No, the primitive were already known. The primitive element, sorry, but the primitive element were already known somehow.
Yeah. So what was not explicitly stated before is that this primitive decomposition turns the Connes-Kreimer Hopf algebra into a B-infinity algebra.
Ah. Okay.
So this is the relation. So we always use that doing this. So taking T of primitives turns the Connes-Kreimer Hopf algebra into B-infinity algebra, and that's why how we can do everything. So basically, both are results about B-infinity algebras.
Yeah.
But it's just that since we're looking at equations, in our case, it really makes sense to look at the. I mean, for example, this kind of expression here. They don't make sense if you have. I mean, you could put an arbitrary B-infinity algebra, and we actually thought about this.
Yeah.
But really, at least as far as I could tell, we did not find a good reason for doing this. But like, if you want to look at equations, you're somehow restricted to Connes-Kreimer. But what we use to prove everything is that Connes-Kreimer is a B-infinity algebra.
Yeah. And then you say, by the way, we found out this thing about commutative B-infinity algebra. But you don't need this for the Itô formula, right? The Itô formula you proved before. Somehow. Or
yeah, I mean, the fact that you can extend in this way as a morphism of algebras without coming from a polymorphism is also dependent on B-infinity. It's because of covariance.
Okay. But it doesn't depend on the Hoffman isomorphism or anything.
No.
Yeah.
But it depends on cofreeness. So this is the whole thing that's underlying the results. It's really, you decompose Connes-Kreimer as a cofree coalgebra, and the product gets twisted. It's not the forest product anymore. It has these contractions, but that's fine. You can handle that.
And also, if you try and write the isomorphism in the forest spaces, you get some very nasty coefficients, whereas it's much more natural to use the cofree basis, the gradient.
Yeah.
Which makes it makes apparent the relationship between this and Hoffman. This is Hoffman plus other things.
Yeah. So So basically what we are saying is that we know some things about B-infinity algebras. They work nicely for some computations you want to do. And look, Connes-Kreimer is one example with this B-infinity product coming from the T operation and the pi one, and then we can proceed. We can calculate stuff.
And you can even build, if I can just finish it, you can even build a stochastic object from that, which is a
yes
kind of
so, yeah. I mean, I didn't have time to go into this, but
in any case, that's really so somehow the right basis to look at branch growth paths is not the trees, but this linear combination of trees.
So the way this example is constructed is really using the decomposition in terms of primitives. Like you cannot really construct it in any other sensible way. Like, because as you said, the forests have like internal relations against themselves. Like you have squares inside, right? You are integrating the square of something, and this primitive decomposition really decomposes these integrals as purely iterated integrals plus some corrections. So it's like you get a shuffle rule more or less, but you need to take care of some extra terms that are handled by the B-infinity property. Yeah, that's basically it. Yeah.
Okay. Any other questions or remarks or observations or comments?
Maybe one more, if you allow. So in Oberwölfach, I already asked this, but I was wondering if you, and I think Emilio had some opinion on this, that identifying these primitive elements somehow, whether one can do this with some simplistic, looking at the simplices, whether there's some language or some geometric interpretation to these guys. Yeah.
Yeah, no, I don't know.
Yeah. Okay.
Yeah, I think we discussed this once, but this is so you can identify relations between the primitives that make it clear that this is Connes-Kreimer is not the free commutative B-infinity algebra. There are some relation. So it's not clear what it's not even clear to me what the free commutative B-infinity algebra, what a presentation of that is.
Like here, right? This guy is antisymmetric in these two labels, and this should not happen in a free B-infinity, because this antisymmetry is not a B-infinity relation. So what this is telling you is you have a B-infinity algebra where you know U V1 V2 is minus it's something like if you flip U and V minus what is it, V1 U V2, and somehow B-infinity is a non-symmetric operator, so you're not allowed to switch variables around. So you always keep them in the same order. In all the B-infinity relations you get, they are always appear in the same order you put them at the beginning. So you're not allowed to exchange the order of the variables. So this relation here is really not coming from B-infinity, it's something else. So it's a relation you have to quotient out. So this Connes-Kreimer, we hoped at some point that it was the free B-infinity, but it's not. The free B-infinity is it's much bigger.
Yeah, I think that it's in Lode and Ronco's paper, not the free B-infinity.
Yeah,
not
I
clear.
mean, yes.
For me, it's not clear, but there are some
suggestions.
me
also it's not clear. I have no
There are
idea.
some suggestions to relate it to in a paper by Lode and Ronco.
Yes, maybe Dominique knows something. I don't know, but
not really. Yeah. Sorry.
No, it's okay. But yeah, I have no idea what the free B-infinity looks like apart from some traces of it I've seen in some papers, but I have no way to yeah.
Okay. If there are no further questions or comments, then I suggest we thank the speaker again.
Thanks very much, Nicolas.
Very nice
Thank
talk.
you.
Thank you, Nicolas. Yeah.
And then hope to see you, let me check, in 2 weeks on the 23rd, then we have Michael Joswig, I think from Berlin, who's going to talk in our seminar.